Hi guys, as I was looking through the homework, I saw some people, or a decent amount of people, were still making mistakes when it comes to drawing resonance contributors and curly arrows and things like that. So I wanted to take a minute to do a couple homework problems with you to point out A, the right way to do it, and B, how I would do it as well. So this is the Chapter 1 homework assignment. If you haven't done this yet, I would recommend you try this homework before watching this video. It's always good to try it first. If you screw up, that's fine. Watch a video, look at answers, talk to friends, whatever the case may be, then go back and try it again. Don't just watch the videos, watch how I do it, and then say, oh yeah, I could do that, because most of the time you think you can, but you actually can't. So here we are, number 37, and we're looking at the first one, letter A. Right, the question is, draw the important resonance forms to show the delocalization of charges in the following ions. So the molecule it gives you is this. I'm going to draw the geometry slightly different than in the textbook, and I'm also going to draw lone pairs because I want it to be absolutely clear exactly what electrons we're talking about. Right? The structure in the book is just given like this, but I want you guys to know that it does have a lone pair of electrons, right? So this one's a relatively simple one, right? Carbon has a negative charge. It's not an electronegative element. It's not a big element. It's not particularly happy having that charge. And so it's looking to offload this charge somewhere. As we'll see about the hybridization and the shape of the orbitals, why this happens. But for now, all we need to know is that carbon with a negative charge, not stable. If we take these two electrons and we push them into this bond, that would violate the octet of this carbon, and so the only way we can maintain a full octet on this carbon is for the carbon-oxygen bond, the pi bond if you remember last lecture, to go to the oxygen. That will give you a resonance contributor. That looks like this. H3C, C. Now it's a single bond. Oxygen still has a full octet. If you calculate its formal charge, you'd end up with -1. Or if you use my shortcut, which I'll tell you in lecture next time, it will be it'll also be -1, but it's just an easier way to determine. We already had a bond here. Now we're using these electrons to make another bond, so we have a double bond, and we have a carbon, and we have a hydrogen. So we get the resonance set that looks like this. This is a more favorable electronic configuration for the molecule because everything still has a full octet, but the negative charge is now on the electronegative oxygen. And so this is the set that it's looking for as the answer for A. Okay. Let's do B. It's also somewhat simple. So, right, you might know how to do these. If you do, great. If not, that's okay. That's why we're learning it right now. And again, I'm going to draw the lone pair of electrons. So there's a couple different resonance contributors you can draw for this one. What I like to do is just move one pair of electrons one place and then see if there's another structure that you can draw after that. So again, same argument. Carbon doesn't like to have a negative charge. It's looking to do something with that negative charge. If we take these electrons and stuff them here, it's the only thing we can do. This carbon would have a violated octet, so the electrons in the pi bond that are right here have to go somewhere. Well, they can go to this carbon and give you the first resonance contributor. That looks like this. Don't forget to draw the lone pairs. Oops, I drew an extra bond by mistake. Where's my eraser? There it is. Okay, and then carbon, hydrogen, double bond to the CH2. Right, so this is one of our contributors. This is not the only contributor because we really haven't changed the game too much. We went from carbon with a negative charge to carbon with a negative charge. Not particularly helpful. It's helpful insofar as not 100% of the charge is on one carbon, rather 50% of the charge is on two carbons. But there's one other thing that we can draw, which is just like the one we just did. Oops, forgot to fill in my electrons. So we get one more resonance contributor that looks like this. I'm running out of space, right? And that would be our resonance set. Right, so if it says draw all the resonance contributors, you would need to draw all three, and you would need to have all four arrows. And unless it specifically says draw the arrows that return to the structure, kind of like quiz 1 said, then you don't need the arrows that do this type of stuff. Right? You wouldn't need these arrows. Alright, so that's B. Let's take a look at C. C is a little different because now we have a positive charge. We have CH2 plus, which means that we're short a lone pair of electrons. The benzyl radical is what this is called. right? And what we're saying is, well, carbon doesn't have any electrons. Remember, arrows always have to start at an electron source. The only electron source that we have, since there's no lone pairs in the structure, is the pi bond. So if I take the electrons that are in this pi bond and I put them here, right, now this carbon will have a full octet, this carbon will still have a full octet, this carbon will now be short 2 electrons. It used to have 2 in the pi bond, and now it doesn't. So it would give you a structure that looks like this. Since it's short 2 electrons, if you calculate the formal charge, you'll end up with a positive charge. And like I said in lecture, whenever you start with, whatever the total charge is that you start with, that has to be the total charge on all the resonance contributors. Otherwise, you messed up. And you can continue to play this game. You can take the electrons from the pi system and scoot it over one bond. That's how far they're allowed to travel, one bond. So you get this, and then the last one you can put there to give you your last set of resonance contributors to look like this. Okay. If you thought this is a lot of contributors, you're right. And when you get to, I think it's chapter 16, electrophilic aromatic substitution reactions, you're going to be drawing lots of these. So might as well get comfortable with the idea now. Alright, so that's that. So remember, the rules for electrons and traveling and drawing arrows and stuff like that is it can go, it can go from a bond, i.e. it used to be a lone pair, and it can go, oh, excuse me, I take that back. It can start at an atom, such as a lone pair on an atom, A-T-O-M, right? And then it can go to a bond. So an example of that would be like carbon that has a lone pair of electrons and another carbon. It can take these electrons and push them in here, as long as we don't violate carbon's octet. Right? Since this carbon, we'll put a positive charge on it. There we go. Something simple like that. The other things that the electrons can do, they can go from a bond to another bond. That's an example of what we did right up here, right? So for example, we went from a bond here to a bond there. So we'll just redraw it again really quick. So we have a positive charge there. We can take the electrons in this bond and put them there, and move the positive charge over there. There's some special names for this, but we'll talk about it in a little bit. So we can go from atom to bond to bond, and we can go from bond to atom. So for example, if we had a carbon-carbon double bond, an alkene, if we remember our nomenclature, we can say, well, technically there's a resonance contributor. These electrons go to this carbon. Not sure why they do that. It's not particularly favorable, but we can draw it. It's a legal structure. Putting a positive charge on this carbon, a negative charge on this carbon, you can see they're probably not going to want to separate, but that is a legal way to draw the resonance structures. Okay, the thing that we cannot do, nope. Right. The thing that we cannot do is we cannot go atom to atom. So that would be bad. Right. So if I try to draw like a carbon with a lone pair of electrons, and then another carbon, and then an oxygen. Let's say the oxygen only has 6 electrons, right? Something like that. I cannot jump around and go all the way over here, right? I'm traveling through too much space. It's just too far away. I can go here, I can go here, and if I'm on the atom, that's all I can do. I can essentially go one location away. I can't go 1, 2, and then another atom away. That's just way too far. So this makes me frown, so make sure you don't do that, okay? So I'll leave the rest of number 37 for you guys to do. I don't want to give you all the answers. Of course, if you have questions, you can ask me in lecture or whatever. Let's take a look at 45. 45 is label the reactants in the acid-base reactions as Lewis acids, aka electrophiles, or Lewis bases, aka nucleophiles. Use curve arrows to show the movement of lone pairs. So the first one starts with methoxide. That's what this is called if you care to know names. Oxygen has a lone pair, 3 lone pairs, negative charge, and it's going to make a bond to that, right? And it actually gives you the product, so I'll draw that too. And chloride. Good. Total charge on the left is the same as total charge on the right, so we're good. So this one is nice and simple, right? What is the bond that we're making? We're making a bond between this oxygen and this carbon, i.e. it's this bond right here, and we're breaking a bond at the same time between this carbon and this chlorine, which is floating away as chloride. So if you notice chlorine over here has 3 lone pairs, 6 electrons, and it's ending up with a negative charge, which means it has 4 lone pairs. So that means it's taking these electrons when it leaves, right? And that makes sense because chlorine is more electronegative than carbon. So if this oxygen says, hey carbon, make me a bond, right? Carbon's like, alright, that's cool, but I can only have 4 bonds, and I already have 4, so I have to get rid of one. Chloride says, no problem, I'll take this bond, go over here, end up like that. We make our new bond right there. Make our new bond right there, and that's our answer, right? Later on we'll learn that this is called an SN2 reaction. Don't worry about that for right now. Alright, let's take a look at B. I think B is a stupid one, actually. That's a dumb example. I'm going to skip and do C. I like C better. Alright, so we have H, C, double bond, O, C. Good electrophile. And this guy. Oops, we forgot to label it. Right? It also says label the acid-base reactions as Lewis acids, electrophiles, or Lewis bases, nucleophiles. Remember, the thing that makes a bond to a non-hydrogen nucleus is the nucleophile. So this would be the nucleophile, and the thing that gains electrons is the electrophile. Right? So this would be our electrophile, that would be our nucleophile. Same thing here. These electrons, our product looks like this. O minus. Until we get in the habit of understanding where all the electrons are and where the charges come from, we should probably draw all of our lone pairs. Okay, so the bond we're making is between the nitrogen and the carbon. That will be this bond right here. So that means these electrons, the arrow starts at the electrons and goes to the carbon atom, and go all the way to the atom, don't be ambiguous. And then the electrons in the carbon-oxygen pi bond will go to the oxygen. Since oxygen is electronegative, it's already pulling electron density its direction anyway, and so these two arrows are the ones that are responsible for making this bond and breaking the double bond and turning it into this single bond right here. That would make this guy the nucleophile. He's the attacker. Nucleophiles attack. That's the language that we use. We'll get into it once we get to chapter 4. And then this would be the electrophile. Electrophiles accept. Okay, so that's a couple examples from 45. Hopefully you can do that for the rest of them. For example, D should be relatively easy. E should be easy. F will be a little bit more questionable, but you can take a look. The last one is 46. Right. Some people struggle with that. Predict the products of the following acid-base reactions. H2SO4. Hopefully everyone immediately recognizes that as a strong acid from Gen Chem, the list of 7 strong acids. An acetate, which is written like this, but the structure, if you actually draw it out, try and draw out the Lewis structure, looks like this. Right? H2SO4, in case we forgot. We don't necessarily have to draw it out, but sometimes it helps. Lots of lone pairs, lone pairs, lone pairs. Okay, so this H is going to bond over here to this H. How do I know that? Well, this is a strong acid, right? It's one of the strongest possible acids. So clearly he's the acid. Clearly he will have to be the base. And the question just says predict the products, right? So this hydrogen will bond to this oxygen. If I wanted to draw the curly arrows, which I should be able to do, I take the lone pair of the oxygen, and I go all the way to the hydrogen to which it's making a bond. Then what happens to these electrons? If the hydrogen's only allowed to have one bond, so if I make a bond to this hydrogen, I have to break the bond. Well, oxygen doesn't mind having a lone pair of electrons, and so you get HOS, double bond O, double bond O, O minus. And on the other side, now he is now neutral, so you get H3C, C double bond O, OH. Total charge on the right, -1. Total charge on the left, -1. World makes sense. Okay, so that's how you do that one. Let's do one that's a little bit more questionable. Let's look at D. That was the one I just did was A, by the way. Let's take a look at D. D says CH3 NH plus OH minus. So OH minus, hydroxide, looks like that, and the question is, what does it give you? This might be a little confusing for you, so let's draw out the structure, right? The nitrogen has 3 methyl groups attached. That's what these parentheses mean. So whatever's inside the parentheses, you have that unit happening 3 times. Okay, so I have a nitrogen, and directly attached to it I have a CH3, and I have another CH3, and I have another CH3. And if I do the rules for counting and stuff, I would see that if I add one more bond to the hydrogen, that would give my nitrogen a positive charge. So this structure, this empirical formula, can be written as this Lewis structure. OH minus doesn't really get much more simple than that. What is the chemistry we're going to do? This is an acid. How do I know? It has a hydrogen bonded to electronegative element. This is a base. How do I know? It has a high energy pair of electrons. Hopefully you remember from Gen Chem that OH is a base, like sodium hydroxide, NaOH, right? It's used as a base. So we take the electrons from the oxygen, we make a bond to the hydrogen. Again, no ambiguity. These electrons then have to be accounted for. Where are they going to go? Well, if the nitrogen is positively charged and it's electronegative, that's a very disfavorable energetic state. And so the electrons will go to the nitrogen, making nitrogen have a neutral charge, giving it a lone pair. The three methyl groups that are hanging out, they're not going to do anything. They're just like, we're methyls, we're cool, don't worry about it. What are we generating in the other side? Water, right? So hopefully this makes sense and you're understanding how to solve these problems. The goal of this video is just to show you kind of what I'm thinking as I'm doing these. Hopefully you should be using the same logical line of reasoning. So do them again if you need to. Do the recommended problems, see if it makes sense to you. If not, let's talk about it in lecture. Don't be afraid to ask questions, because if you don't know how to do it, I guarantee there's at least 5 other people in class that are thinking the same thing, but they don't want to raise their hand. You can always, of course, send me an email and say, hey, can you clarify this? And if I get a whole bunch of emails from people that say, hey, clarify this, and it's all the same thing, then we should go over it. All right, guys, good luck. Have a good weekend. I'll see you on Monday.